For decades, the world of computing followed a simple rule: make chips smaller, faster, and more powerful. This strategy fueled the digital revolution, enabled the internet, powered smartphones, and ultimately gave rise to artificial intelligence. But today, that model is reaching its limits. AI systems are becoming so large, so complex, and so energy-hungry that the hardware supporting them is struggling to keep up. The next stage of artificial intelligence may depend not on better software, but on an entirely different kind of computer. Modern AI runs on hardware originally designed for very different purposes. Most computers still rely on a structure known as the von Neumann architecture, named after mathematician John von Neumann. In this design, memory and processing are separated. Data must constantly move back and forth between storage and the processor. For everyday tasks, this works well. For artificial intelligence, however, it creates a growing problem. The issue is often called the von Neumann bottleneck. Every calculation requires data to travel between memory and computation units. As AI models become larger, this movement consumes enormous amounts of energy and time. In many cases, the transfer of information requires more power than the actual calculations themselves. The result is an architecture increasingly strained by the demands of modern machine learning. This challenge is becoming visible across the technology industry. Training advanced AI models now requires vast data centers filled with specialized hardware. Some facilities consume electricity on the scale of small towns. As AI expands into search engines, robotics, autonomous vehicles, scientific research, healthcare, and military systems, energy demand continues to grow. The future cannot rely indefinitely on simply building larger facilities and consuming more power. Nature solved a similar problem millions of years ago. The human brain performs extraordinary tasks while consuming roughly 20 watts of power. That is less electricity than many household light bulbs. Yet the brain continuously processes sensory information, controls movement, recognizes patterns, learns sins from experience, stores memories, and makes decisions in real time. Modern supercomputers require vastly more energy to perform only a fraction of these capabilities. This comparison has inspired a new field known as neuromorphic computing. Rather than forcing AI to operate on traditional computer architectures, neuromorphic engineers attempt to build hardware that functions more like biological nervous systems. The goal is not to copy the brain perfectly. The goal is to borrow the principles that make biological intelligence so energy efficient. Traditional computers process information using binary states. Every operation ultimately reduces to combinations of ones and zeros. Neuromorphic systems operate differently. They use structures inspired by neurons and synapses, the fundamental components of biological brains. Instead of constantly processing information, these systems often remain inactive until meaningful signals arrive. This event-driven approach dramatically reduces energy consumption. One of the most important concepts in neuromorphic computing is the spiking neural network. Conventional artificial neural networks process information continuously across multiple layers. Spiking networks communicate using pulses or spikes, more closely resembling the behavior of biological neurons. Information is transmitted only when necessary, allowing computation to occur with far greater efficiency. Researchers have already demonstrated promising results. Several neuromorphic chips can perform pattern recognition, object detection, and sensor processing tasks using a tiny fraction of the energy required by traditional processors. While these systems remain specialized, they demonstrate the potential for dramatically lower power consumption. Major technology organizations are investing heavily in this field. Companies, universities, and government research agencies recognize that current AI growth rates may become unsustainable without significant improvements in efficiency. The challenge is not merely computational power, it is computational power relative to energy consumption. This issue becomes especially important for autonomous systems. Self-driving vehicles, drones, robots, and industrial machines cannot always rely on large cloud data centers. They require local intelligence operating under strict power constraints. A robot exploring a disaster zone or a drone monitoring infrastructure cannot carry a power plant with it. Neuromorphic hardware offers a potential solution. The military is also interested in these technologies. Modern defense systems increasingly depend on artificial intelligence for navigation, surveillance, target recognition, electronic warfare, and decision support. Energy-efficient processing could allow advanced AI capabilities to operate in remote environments where power resources are limited. Space exploration provides another example. Spacecraft and planetary rovers operate under extreme power restrictions. Every watt matters. A neuromorphic system capable of intelligent decision-making while consuming minimal energy could dramatically improve the capabilities of future missions. Healthcare may benefit as well. Medical devices increasingly incorporate artificial intelligence for diagnostics, monitoring, and treatment assistance. Energy-efficient hardware could support continuous patient monitoring systems, advanced prosthetics, brain-computer interfaces, and wearable medical technologies without requiring frequent charging. The relationship between neuromorphic computing and artificial intelligence is particularly important because AI itself is evolving. Today's large language models, image generators, and predictive systems depend heavily on massive computational resources. Future AI applications may require even greater efficiency as they move beyond data centers into everyday environments. However, neuromorphic computing is not simply about reducing electricity bills. It may also enable entirely new forms of intelligence. Biological brains excel at tasks that remain difficult for traditional computers. Humans can learn from small amounts of data, adapt rapidly to changing environments, recognize patterns under uncertainty, and operate effectively despite incomplete information. Neuromorphic systems may eventually help bridge some of these gaps. One reason biological systems perform so efficiently is that memory and computation occur together. In the brain, information storage and information processing are deeply integrated. Traditional computers separate these functions. Neuromorphic architectures attempt to reduce this separation, minimizing the costly movement of data. Researchers are exploring new materials and devices to support these goals. Memristers, for example, are electronic components capable of retaining memory while performing computation. Such technologies could eventually allow hardware to function more like biological synapses. While still developing, these approaches may form the foundation of future computing systems. Challenges remain significant. Neuromorphic computing is still a relatively young field compared with traditional semiconductor engineering. Programming these systems requires new software tools, new algorithms, and new ways of thinking about computation. Engineers must often redesign applications entirely to take advantage of neuromorphic architectures. Compatibility is another challenge. The digital world is built upon decades of software designed for conventional computers. Transitioning to fundamentally different hardware cannot happen overnight. Neuromorphic systems will likely coexist with traditional processors for many years rather than replacing them completely. Nevertheless, momentum continues building. As artificial intelligence expands, energy efficiency becomes increasingly important. The economics are impossible to ignore. Data center operators, governments, and technology companies all face rising energy costs. Improving efficiency is no longer simply desirable. It is becoming essential. Some experts compare the current moment to the early days of aviation. The first aircraft were not immediately practical replacements for trains or ships. Yet they introduced principles that eventually transformed transportation. Neuromorphic computing may represent a similar shift. Early systems may appear specialized today, but their underlying principles could reshape the future of computing. The broader significance extends beyond artificial intelligence. Modern civilization increasingly depends on digital infrastructure. Communication networks, transportation systems, financial markets, healthcare, scientific research, and industrial operations all rely on computation. More efficient hardware could influence every one of these sectors. What makes neuromorphic computing particularly compelling is that it challenges a long-standing assumption. For decades, progress meant building faster machines through greater complexity and higher power consumption. Neuromorphic engineers are pursuing a different path. Instead of forcing intelligence to conform to machines, they are redesigning machines to reflect the principles of intelligence itself. The future of AI may therefore depend less on creating larger models and more on creating smarter hardware. The next breakthrough may not come from another software update or a larger data center. It may come from a computer that processes information the way nature has done for millions of years. The Silicon Revolution transformed the modern world. Neuromorphic computing may represent the next chapter. As traditional architectures approach their limits, engineers are turning to biology for inspiration. In doing so, they may unlock a future where artificial intelligence becomes vastly more powerful while consuming only a fraction of the energy required today. If you enjoyed this deep dive into the forces shaping our future, be sure to explore our other documentaries examining the technologies redefining modern civilization. And if you want to keep exploring the biggest questions about science, power, and the future of humanity, make sure to subscribe to the channel and join us for the next journey into the unknown.